Hello and good morning to all of you. I hope all of you are doing well and all of you are in good health. In today's class, we will discuss deadlock avoidance. Deadlock avoidance is a mechanism used by the operating system in order to avoid deadlocks. Now, let us try and understand how an operating system does the same. The operating system initially determines the maximum resource requirement of all the processes, and it also determines information regarding available free resources. So taking into account these two valuable informations, the operating system makes quality judgment regarding the way how the allocation is to be performed so that deadlock can be avoided. So here operating system takes into account the maximum resource requirement and the available resources in order to make quality judgment about the way how the allocation is to be done so that deadlock can be avoided. Now how does it do it? So operating system attempts to allocate the resources accordingly to the process requirement by determining if the allocation leads to a safe state or an unsafe state. Again, I'm repeating it. Operating system attempts to allocate the resource accordingly to the process requirement by determining if the allocation leads to a safe state or an unsafe state. Now here safe state basically refers to a state of allocation sequence wherein we will not encounter deadlock, whereas unsafe state refers to an allocation sequence which may or may not lead to a deadlock. So again, I'm repeating it. Safe state refers to an allocation sequence wherein we'll never encounter a deadlock, whereas unsafe state refers to an allocation sequence which may or may not lead to deadlock. So OS or the operating system attempts to allocate the resources accordingly to the process requirement by determining if the allocation leads to safe state or an unsafe state. Now once the operating system has determined that the allocation sequence results in a safe state, then the operating system proceeds ahead with the allocation, and if it determines that an allocation sequence may lead to an unsafe state, then definitely operating system stops the allocation process. So in situation if the resource allocation leads to safe state, then the operating system proceeds with the allocation sequence, otherwise the operating system stops the allocation process. So this is the way how an operating system avoids deadlock. Now let us try and define safe and unsafe state. Now safe state: if an operating system is able to allocate or satisfy the maximum resource requirement of all the processes in the system in any order, then the system is said to be in safe state. Again, I'm repeating it. If an operating system is able to allocate or satisfy the maximum resource requirement of all the processes in a system in an order, in a system in any order, then the system is said to be in a safe state. So safe state does not lead to deadlock. So this is what safe state is all about. So if an operating system follows an allocation sequence that does not lead to deadlock, then it's called as a safe state. Now likewise, let us define unsafe state. So if an operating system is unable to prevent processes from requesting resources which may lead to deadlock, then the system is said to be in unsafe state. But here we need to understand that unsafe state does not necessarily cause deadlock. It may or may not cause deadlock. So this is to be understood. Unsafe state does not mean that it will lead to deadlock, but it may lead to deadlock. So if an operating system is unable to prevent processes from requesting resources which may lead to deadlock, then the system is said to be in an unsafe state. So here we have a very simple schematic representation that shows distinction between unsafe state and a safe state. So in safe state we will not have any deadlock, whereas in case of unsafe state there is a probability of deadlock occurring. Now let us try and understand the same with the help of a very simple example. So here we have 4 processes in the process set: P1, P2, P3, P4, and we have multiple instances of a resource, right? We have multiple instances of resource R. So here the maximum resource requirement of P1 is 9, Likewise 7, 5 and 3 for P2, P3 and P4 respectively. So 9, 7, 5, 3 are the resource requirement of P1, P2, P3, P4 respectively. As per the current allocation, P1, P2, P3, P4 holds 4, 3, 2, 1 resources respectively. So there are 4 resources allocated to P1, 3 resources allocated to P2, 2 resources allocated to P3 and 1 resource allocated to P4. So taking into cognition these information, the need is determined. So need for P1 will be 9 minus 4, that is 5. For P2 it's 7 minus 3, 4. For P3 it's 5 minus 2, 3. For P4 it is 3 minus 1, 2. So this is the current status of allocation and need of the 4 processes that are there in the system. Now let us assume there are only 2 resources available. So here we are assuming that there are only 2 resources available. So now we need to make a quality decision about the way how these 2 resources are to be utilized so that we will not enter into a state of deadlock. So here we need to determine that how judiciously these 2 resources can be allocated to the processes so that we will not have a deadlock. So out of the 4 processes P1, P2, P3, P4, we see that there is a resource P4 that requires 2 resources, or that requires 2 resources for completion. So here what we do is we allocate 2 to P4. So once 2 is allocated to P4, then P4 2 meets the requirement of P4, that is 2. So after executing or after completing its execution, P4 will not only release the resource, 2 resources that was assigned to it, but it will also release the resources that it was holding prior to it. So prior to execution or prior to completion, P1 was holding 1 instance of resource, so it will release that as well. So now here after completion of P4, the total number of resources that will be available will be 3. Why 3? Because 2 was assigned to it and 1 it was holding. So on completion of its execution, it will release all the resources. So it will be 2 plus 1, that is equals to 3. Now we have 3 resources in hand. So now there are 3 processes that are yet to complete its execution. So out of the process set, P4 has already completed its execution. We have P2, P1, P2 and P3. So if you see, there is a process P3 that requires 3 instances of resources. So now what we'll do is we'll assign these 3 instances of resources to P3. So once 3 instances of resources are assigned to P3, P3 will complete its execution. It will not only release 3, but it will also release the resources that it was holding prior to its completion. So it was holding 2 resources, so 2 plus 3 will be 5. So P3 on completion will release 5 instances of resources. So with 5, we have 2 more processes to complete, P1 and P2. So we see that we can satisfy P1 as well as P2 with 5 instances of resources. So we can select the process in any sequence. So here what I have done, I have selected P2. So P2 is assigned with 5 resources. So now here P2 will finish its execution. It will not only release the resource that is assigned to it, but it will also release the instance of resource that it was holding. So it was holding 3 instances of resource. So 5 plus 3 makes 8. So now there are 8 resources available with P4, P3 and P2 having completed its execution, and we have left with 1 process, that is P1. So now as we see that with 8 instances of resources we can satisfy the requirement of P1. So now P1 will complete its execution. So now all the resource set will be freed. So it will be 8 plus 4. So 8 plus 4 is equals to 12. So we have 12 instances of resource available free that can be used by some other process, and we have successfully executed all the processes that are there that was to be executed, P1, P2, P3, P4, without any possibility of deadlock. So this is the way how deadlock avoidance works. So here we make a qualitative judgment about the way how the allocation sequence is to be pursued in order to avoid deadlock from happening in a system. So here the allocation sequence is P1, P2, P3, P4. It could have been P1, P2, P4 and P3. So based on your requirements. So this is the way how deadlock avoidance works. Now let us consider another example. So here we have four processes again, P1, P2, P3, P4. With maximum request, right? We have maximum requests. So maximum request is 9753. Current holding is 4321, and need we have determined is 5432. So here we have taken the same example of that of the previous case. So here we have four processes again with maximum set of maximum requirements. We have a set of current holdings and we have the need determined. Now let us assume that there is only one resource available. So here in the previous instance there were two resources available. Here in this particular instance you have only one resource available. So now with one resource available, what we cannot do is we cannot satisfy the requirement of either P4, P3, P2, P1. So we cannot satisfy the requirement of any of the four processes utilizing one instance of the resource. So in this situation, the system is destined to enter into a state of deadlock, because any allocation sequence pursued will not be able to prevent system from entering into deadlock. So this is the way how this is the way how deadlock avoidance may fail, or it may lead to deadlock. So these are two typical examples, right? Okay, so of a successful allocation and an unsuccessful allocation. Now let us consider a little complex problem. So here let us consider we have three processes, P1, P2, P3 in the process set, and we have four resources, resource 1, resource 2, resource 3 and resource 4 in the resource set. So we have the process set and we have the resource set, and we have made the resource requirement of each of the processes. So here we have resource requirement of each of the processes. We have resource requirement for P1, we have resource requirement for P2, we have resource requirement for P3. So resource requirements is in terms of R1, R2, R3, R4. So P1 requires 3232 instance of R1, R2, R3, R4 respectively. P2 requires 2314 instance of R1, R2, R3, R4 respectively. P3 requires 3150 instance of R1, R2, R3, R4 respectively. So this is a very simple matrix that represents the resource requirement of the individual processes P1, P2, P3. And let us assume that we have in the resource set R1, R2, R3, R4 with the number of instances 7454. So 7454 are the number of instances of R1, R2, R3, R4 respectively. So here now what we need to do is we need to try to allocate the resources to the processes so that we can avoid deadlock. Now let us consider the current allocation status of processes P1, P2, P3 are as follows. So P1 is allocated 1, 2, 3, 1 of R1, R2, R3, R4. P2 is allocated 2, 1, 0, 2 of R1, R2, R3, R4. P3 is allocated 2, 0, 1, 0 of R1, R2, R3, R4 respectively. So these are the number of instances of resources that are allocated to P1, P2, P3 respectively. Now you have the total number of instances that has already been allocated. So out of the resource set 5343, number of instances of R1, R2, R3, R4 has been allocated as per the current status. So now after the allocation, the resources that are available are, so we have two instances of R1, we have one instance of R2, we have one instance of R3 and we have one instance of R4. So this is formed after determining the difference between the total number of resource instances and the current allocation status. So since if you consider here there are 5 instances of R1 that is allocated, so 7 minus 5 will be 2. So this is the way how the resource set is determined after allocation. So we have two instances of R1, one instance of R2, one instance of R3, and one instance of R4. So we have 2, 1, 1, 1 number of resources of R1, R2, R3, R4, and then we need to attempt to allocate these leftover resources in a manner that we do not have deadlock in the system. So as we have already learned about, need is equals to maximum minus the current allocation. So here what we have is we have the need determined, right? Okay, so we have the need determined. So need for P1 is 2101, need for P2 is 0212, need for P3 is 1140. Now this is determined after subtracting maximum resource requirement and current allocation. So here we have the current allocation and we have the maximum resource requirement here, right? So 3 minus 1 will be, say for an example, 2. So in case of this is a very simple matrix that is formed after subtracting the maximum resource requirement and the current allocated resources. So if you subtract current allocated resources from maximum resource requirement, so you will get this particular matrix. So if you would try the same with the maximum resource requirement and the current allocation resources, so you will get the same matrix. So this is the need matrix, the number of instances of resources the processes will currently need after allocation. So now what we need to do is we need to try to satisfy the processes so that we enter into a safe state in a manner that the available resources are utilized. So now there are 2111 instances of resource R1, R2, R3, R4 available. So this we have already determined. So here we have 2111 instances of resource R1, R2, R3, R4 available with us. So with this available resource, what we need to do is we need to try to allocate resources to the processes in a manner that we will not have deadlock. So if you closely analyze, there is a process P1 which requires 2101 instance of resources. So with 2111 instance of resources, what we can do is we can satisfy the requirement of P1. So what we'll do is we'll assign 2111 to P1, right? So we'll assign 2111 to P1. So now P1 is allocated the resources. So once P1 is allocated the resource, P1 will complete its execution. It will not only release the resource that is being assigned to it, but it will also release the resource it was previously holding. So it was previously holding 1231 instance of resource. So now in totality there will be 3342 instance of resource R1, R2, R3, R4 respectively left with the system that can be assigned to other processes, right? Okay, so from where 1231 was derived, so 1231 was derived from here. So here P1 has been allocated resources 1231. So 1231 instances of resources were already allocated to P1. So when 2111 instance of resource was allocated to P1, then it will release the assigned resource, as well as it will release the resource that it was previously holding after its execution is over. So the total number of instances of resources that are now available with the system is 3342. So after completion of process P1, you will have 3 instances of R1, 3 instances of R2, 4 instances of R3, and 2 instances of R1. Now we need to determine which one out of the 2 processes that are left to complete its execution can be assigned this leftover resource so that it will complete its execution. So we have 2 processes that are left, P2 and P3. So P2 requires 0 to 1 2 instance of R1, R2, R3, R4, and P3 requires 1140 instance of R1, R2, R3, R4. Right? Okay. So now here what we see that P1 is already over. Now P2 requires 0 to 1 2. So can we satisfy 0 to 1 2 with 3 3 4 2? Yes, right? So P2 can be initiated. Likewise P3. So P3 requires 1140. So 1140 can also be satisfied within 3342. So what you can do is you can select either P2 or P3 in order to proceed with the allocation sequence, right? So we can either select P2 or either select P3 for proceeding with the allocation sequence. So here what I've done is I've selected P2. So once P2 is selected, the resources that are available 3342 are assigned to P2. Once P2 completes its execution, it will not only release the resource that is assigned to it, but it will also release the resource that it was previously holding. So previously it was holding 2102 instance of resources. So now it will be 3342 plus 2102 instance of resources. In total it will be 5444 instance of R1, R2, R3, R4 available with the system that can be used by another process. Now out of P1, P2, P3, P1 and P2 has already completed its execution. Now we are left with P3. So P3 is assigned with 5444. So with this assignment, P3 will complete its execution. So once P3 will complete its execution, it will release all the resources. That is the resources that was assigned to it, as well as the resources that it was previously holding, right? So it will release both the set of resources. So in total now the system will have 7454 instances of available resource, right, with P1, P2, P3 having completed its execution. So here I've selected the sequence P1, P2, P3. You can also select the sequence P1, P3, P2. So in either ways we will not have deadlock in the system. So here what we have learned in today's classes, we have learned about what is deadlock avoidance, right? We have learned about what does the operating system do in order to avoid deadlock. We have learned about what is safe state and unsafe state. Then we moved on with the definition of safe state and unsafe state, where we try to understand safe state and unsafe state with the help of a very neat schematic representation. Then we try to discuss example by taking into consideration process set and the allocation set, and then determining the need. So with the number of instances of resources available, we try to determine whether deadlock will be there or not, and then proceed with the allocation sequence. Then we took a little complex example to understand the way how deadlock avoidance basically works, where we considered three processes with four types of resources with different number of resource instances. So we learned about the way how the allocation sequence is to proceed in order to avoid deadlock. So in the next class we will discuss a very important algorithm in deadlock avoidance that is called as Banker's algorithm. Till then, thank you very much and have a good day.